On the other hand, if I had some kind of way of saying, well, this clip is a standard, so if I somehow know that x, let's say for sake of argument, is, let's make it minus 0.2. If I somehow know that x is equal to minus 0.2, that is, if the actual clip size is 32.000 minus 0.2, that is, if it's 31.8, I can use that together with this confidence interval to estimate the bias of my measurements. So if I know this, this can be used to estimate beta. Why is that? Well, I'm claiming that x plus beta has limits of minus 0.051 plus or minus 0.0032. I'm claiming that I know that to be minus 0.2, so that implies that beta has limits that are this minus 0.051 plus 0.2 plus or minus 0.0032. So the point is that if I know that the instrument's calibrated or well calibrated, bias is 0, then the good old Stat 231 method gives me a way to estimate the actual measure end. If I instead know that I'm measuring a standard, the Stat 231 method gives me a way of estimating bias. What about this set of confidence limits for a standard deviation? Well, if I take limits s square root of n minus 1 over an upper chi-square value and s square root of n minus 1 over a lower chi-square value, in this particular context, that says take 0.0035 and multiply by 7 minus 1 over, well, for sake of argument, let's make 90% limits in this particular case, just to illustrate a different confidence level. What I need here is an upper 5% point of the chi-square distribution. Chi-square distribution with 6 degrees of freedom. And if I look in a chi-square table, that's 12.592. That's a lower confidence bound. If I take 0.0035, I multiply by the square root of 7 minus 1 over an upper 5% point of the chi-square 6 distribution. That is 1.635. I get limits that are 0.0024 up to 0.000067, and the units are millimeters. What are these? These are limits for this Sigma device, this thing that measures basically how consistent my measurement system is, how consistent what kind of spread I have in the distribution of measurements for a fixed measure hand.